So in the last class, I mentioned the BVP problems. That means a boundary value problems. Okay. I would like to write down the problem again in case you already forget it. Boundary value problems. We just have the second order differential equation. YB equals Y1. And the second one is we have 4 scenarios for the boundary condition. Force. Okay, we have 4 scenarios. We have 4 scenarios for the boundary condition. Given the second order differential equation, we usually have 2 boundary conditions, and we can. I would like to mention again, for the boundary value problems, if I give you one second order differential equations, we can have infinity solutions, right? We can have many solutions. One example is last time I mentioned this guy. And today we're going to continue this example. Okay. One example last time I gave you is C1 cosine 4t C2 sine 4t is the solution of this guy. Okay. And for the first condition, for this case, from last class, we know we have we find that is this guy. Okay, we find this guy through these 2 conditions. We find that the solution is here. Okay, and that means we have many solutions. Okay, that's what we did from the last class. Okay, we found given these 2 conditions, we find that the solution is x equals C2 sine 4t, and that means we have many solutions because C2 can be any real number. Okay, any real number. Okay, so today we're going to continue our journey. Now, B. If I give you condition, okay, how to find the solution? How to find the solution? What are we gonna do? Yes, the same things. Okay, so the first things we're gonna plug in is the first condition to here. The first condition gonna be when x or when t equals 0, x equals 0. Right? So you can plug in equals 0. That's the first condition. And the second condition gonna be what? When t equals pi over 8 and x equals 0. So we can plug in cosine 4 times pi over 8. Sin 4 times pi over 8. And this guy gives us z 0. Okay, 0. Very good, very good. So now from the first one, we can say cosine 0 equals 1, right? Sine 0 is 0. Okay, and then we can tell this guy equals 0. And from condition 2 is C1 cosine pi over 2, C2 sine pi over 2 equals 0. Okay. So for this equation, cosine pi over 2 is 0, right? Cosine pi over 2, cosine 90 is 0, right? And the C2 sine 90 is 1. So we can get C2 equals 0. Okay. So we get C1 equals 0, C2 equals 0. And that means we're going to plug in back here. Plug in back. C1 is 0, C2 is 0. So we have x equals 0 is the x equals 0 is the solution of BVP problems. Okay. So that for this case, we have only one solution. We have only one solution. It's different from the first scenario. If I give you these two conditions, we have infinity solutions. Right? So now I want you guys try these conditions. I'm gonna change this condition. Okay, try it again by yourself. I'm gonna give you guys 1 or 2 minutes. 2 minutes, okay? Try it by yourself. Okay, now let me do it. Okay, so for this case, x0 equals 0, the same things, right? Like the last condition, we can plug in the 0. C1 cosine 4 times 0 plus C2 sine 4 times 0. Okay, and the second condition, sine cosine 4 times pi over 2 C2 sine 4 times pi over 2. Right. And from the first condition, we know from the last example, we know the C1 equals 0, right? C1 equals 0. Now let's take a look at the second condition. Second condition, we have C1 cosine 2 pi, C2 sine 2 pi. Okay, and as we can see, cosine 2 pi is 1, right? And oh, here's 1. Sorry. Here, give us the condition is 1. Okay. So, and the sine 2 pi is 0, right? And we got, yeah, C1 equals 1. Now we can see from the first condition, C1 is 0. And for the second condition, C1 equals 1. That means what? That means contradict each other, right? Contradict each other. So this BVP has no solution. Okay, contradict each other because the first condition gives us C1 equals 0. The second condition gives us C1 equals 1. These two contradicts each other. Okay, so for our BVP problems, as I mentioned before, if I give you a conditions, two conditions, there can be one solution or two solutions or one solution or no solution or many solutions. Okay, so we have 3 scenarios for the BVP problems. Okay. Okay, let's continue. Today we're gonna go to section 4.1.2. Homogeneous equations for linear nth order differential equations. We have what? We have ANX and AN minus 1, blah, 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 blah. Where Gx doesn't equal 0, okay? And we call this one as non-homogeneous. second one. We have this guy. Dy over dx. A0 x y equals 0. Okay. And we call this one is homogeneous. Or we can write down the solution for the non-homogeneous can be write down as y equals yc plus yp. Okay, so that's what we learned before. For the homogeneous equation, if we get the solution yc, we call a homogeneous solution for this homogeneous equation. Okay, and for the non-homogeneous, we need what? We need to find a particular solution. Okay, a particular solution. Let yc plus one particular solution. We're gonna get the solution for the non-homogeneous equation. Okay, and for this guy, we can write the solution is y equal to yc. Okay. So homogeneous or non-homogeneous, the basic idea is whether the gx equals 0 or not. If it's non-zero, that means that's non-homogeneous. Okay, non-homogeneous. That's what we learned before. Now let's take a look. An example. For the example here. So for example, for this guy, is that a homogeneous or non-homogeneous? Of course, it is a homogeneous because the gx equals 0, right? Gx equals 0. So we can see it's a homogeneous linear second order differential equation. Okay, differential equation. So that's the homogeneous. Now, let's take a look at this guy. How about this guy? Is it homogeneous or not? It's non-homogeneous. Okay, for this guy, it's non-homogeneous because we say we have the x terms. Okay, so we can move this term to the right-hand side. Okay, and this guy is the gx, right? Because for the left-hand side, we require to have the y variables, right? This guy y divided with the x, right? Here we have x terms, so we need to move this term to the right-hand side. So that is a typical non-homogeneous linear third order, because the highest order is third, or the highest derivative is third, right? Okay, now, so that's the basic idea about the homogeneous or non-homogeneous. And today we're gonna learn a very special operators would use different symbols to represent the differential operators. So let's take a look. The first one. Differential operators. If I write down dy over dx, we can write down it's like that. And this part, we can use the capital D, okay? And the D is d over dx. We called differential operator. Okay. And for second derivative, we can write it down as this way. Take a look. We can write down d over dx, dy over dx. Yeah. And d over dx, d over dx, y, right? And the d over dx can be write down d. So we have d dy. Okay. So for the second derivative, we can write down as d squared y. Okay. And for now, if we have n derivative, what we can write down? That's gonna be dn y. Okay, very straightforward. So for the first derivative, 1d. Second derivative, d squared. N derivative, d to the power n. Okay, so that's the rule. Okay, that's the rule. We define the symbol d to represent differential operator. Okay, differential operator. Now, if I give you guys the differential equation, how to use the d to represent the differential equation. So for example, how to represent we can either write down it's like that. D2 by dy. Okay, that's it. That's it. Now I'm gonna let you guys try it. Okay. So second derivative of d squared, further derivative of 1d, right? So I just let you guys try these two. Try these two. Try this one for me. Okay, just try it. Use the d to represent the derivative. Okay. Okay, now let me write down the answer for you guys. So let's take a look. The first one. Fine, for the fourth one. So fourth one, we can write down d square y 3dy. 2. For the second one will be d cubed y 6dy plus 10x equals 0. That's it. Okay, just replace the derivative by the d. Okay, replace the derivative by the d. So here's a second derivative, d squared. First derivative, just d. And if we have third derivative, that means d cubed. Okay, that's it. That's it. Now, for the nth order differential operator, we can use another symbol. Let's take a look. Nth order differential operator. Okay, for the nth differential operator, we can write down as L. Okay, L. L. So for the case of the non-homogeneous equation, okay, the equation 1, we can write down as this way. Okay, we can write down as Ly equals, because this part is L, okay, L. So we write down the Ly equals Gx, okay, equals Gx. That is nth order differential operator. We use the L to represent, okay, nth order differential equations. So we can write nth order, that means this part, right? Put a y here, and we equals the Gx, okay? And then for the second homogeneous equation, we're gonna write down as Ly equals 0, right? Because right hand side is 0. Okay, that's it. That's it. And now let's take a look at the property. Okay, the property for the differential operator. Okay, and 3. The third. And the beta. Okay, and the first one is very easy to understand. If we have a coefficient that is constant, you can move the constant outside. Okay, or you can say, hey, when you do the derivative with constant multiply a function, you always can put a constant outside of derivative. So the second one is sum rule. Okay, if you do the derivative of the summation of two functions, and you can do the derivative for each term. Okay, and the last one, sorry, that is L. Okay, and if we have a coefficient, of course, you can put the coefficient outside and do the derivative for each term. Okay, for the derivative for each term. Okay. Now let's move forward. Principle. Theorem. One point two. Superposition principle. Homogeneous equation. Okay. Let y1, y2, blah 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 blah, yk be solutions of the homogeneous nth order differential equations to on an interval I, then the linear combination is y equals c1 times y1x, c2 y2x, blah blah blah, ck ykx, where I equals 2 blah 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 k are arbitrary constants. Okay, that means can be any real number. Also a solution on the interval. Okay, so let's take a look at the theorem. So if I give you a homogeneous solution, y1, y2, blah 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 blah, we have k solutions. Okay, k solutions. Then if you do the linear combination of these k solutions, okay, do the linear combination of these k solutions, we can construct a new solution, and that is the solution on the interval. Okay, this guy is another solution for this homogeneous equation. Okay, so if you find the k solutions and you use the linear combination of this k solution, that's a new solution for this homogeneous equation. Okay, now Corollaries. A constant multiple y equals c1 of a solution, y1x of a homogeneous linear equation linear differential equation is also solution E. A homogeneous linear differential equation always possesses um, possesses the trivial solution. Okay, that's two important corollaries. Okay, corollaries. So if we find one solution for the homogeneous equation, and if you times the constant, that guy is still the solution of the homogeneous linear differential equations. Okay, and the other one is for any homogeneous linear differential equation, we always have the trivial solution, y equals 0. Y equals 0 is always the solution for the homogeneous equations. Why is that? Take a look. Take a look. So if y equals 0, if you do the derivative, always equals 0. Y equals 0. If you do the derivative of 0, always equals 0. Right? And here is y equals 0. So everything equals 0. Okay? So for any homogeneous equation, we always have trivial solution, y equals 0. And that can be seen from this homogeneous equation, right? If you plug in 0, always give you 0, right? Okay, now, as we mentioned before, if I give you k solutions, we can do the linear combination and construct a new solution, right? So now let's take a look. The example. The solutions. Okay. Since we know for these differential equations, okay, we have two solutions. And for example, we already found the two solutions here. And then according to this theorem, if we do the linear combination, then we can find the new solution. Okay, so basically what are we gonna do? Just follow the theorem. All right, follow the theorem. It's a linear combination. Right? So we have and this guy is the solution of equation. Okay, the solution of equation. Now I'm gonna give you guys an example. Let you guys try it. How about this guy? What is the solution for this guy? Think about it. Okay, let me give you guys a solution. So here we have only one solution, y1, right? So basically what are we gonna do? Y equal to C1 times Y1. That's it. We don't have second solution, right? If you will have third, gonna be a if we have second solution, gonna be C1 times Y1 plus C2 times Y2. If we have third solution, gonna be a C3 times Y3. But here we have only one solution, just C1 times Y1. So just plug in here. Is the solution of equation. That's it. Okay, that's the theorem 4.1.2. Okay, 1.2. Okay, I think it's a very straightforward. It's not too hard. Okay, just do the linear combination of these solutions. Now let's continue. And the second one is a little bit tougher. And but if you learn the linear, have studied the linear algebra, it should be easy for you because we already learned such things before. Let's take a look at the definition of the linearly independent. Definition: a set of functions f(1x) is linearly independent on an interval if the set only has only constant for which C1 f(1x), C2 f(2x), Cn equals x equals 0 for every x in the interval R equals 0. Okay. Otherwise, if there exist constants C1, C2, Cn, not all 0. Okay. And the set is linearly dependent. Okay, linearly dependent. So let's take a look at this definition. Linearly independent. What's the meaning of linearly independent for a set of functions of these guys? That means when we do the linear combination, let the linear combination equals 0, and we solve this equation. Okay, we solve the equation. We find C1 equals C2 equals blah, blah, blah. All the constants equals 0. Okay, we find all the constants equals 0. That means that is linearly independent. Otherwise, if we find non-zero constant, That means it's linearly dependent. Okay. So how to check whether these functions are linearly independent or dependent? Just solve these equations. Do the linear combination let equals 0 and solve this equation to find the constants. If the constants are equal to 0, that means linearly independent. If constants are non-zero, that means linearly dependent. Okay, dependent. So let's take a look at a very specific example. Linearly dependent or linearly independent on the interval. Okay, so how to check whether these functions are linearly independent or dependent? What you're gonna do, just do like that. Follow this definition, right? We construct the linear combination, right? And let this guy equal 0. So what are we gonna do? C1 and then we have what? We have equals 0. And then we can simplify it, right? We plug in these 4 equations and we simplify it. Now we can combine the terms. So from the highest degree, here is C4. Okay. And then X we have 2 terms, right? C3. And square root of X. Okay. And then the constants. Okay, the constants. Now, in order to let this equation equal 0, what does that mean? The coefficient equals 0. Coefficient equals 0. That means what? That means C4 equals 0, right? We let this equation equals 0. That means all the coefficients equals 0. Then we can make sure this equation equals 0. So let's check. Phi C2 plus C3 equals 0. And C1 plus C2 equals 0. Phi C1 plus C3 equals 0. Okay. And from equation 1, we know C4 equals 0, right? C4 equals 0. And from equation 2, we can see, from equation 3, for example, we know C1 equal, C2 equals negative C1, okay? C2 equals negative C1, okay? And then you can plug in, right? You can plug in the C2 equals negative C1 to equation 2. Equation 2. We plug in the 5C2, plug in negative C1, right? You can find what? Negative 5C1 plus C3 equals 0. And the C3 equals 5C1, okay? And from equation 4, we can see C3 equals 5C1. Okay, so you can see what? You can see the solution is what? The solution is C2 equals negative C1 and C3 equals 5C1 and C4 equals 0, okay? And as we know, C1 can be any constant, okay? And C1 can be any constants. That means what? Based on the definition. That means what? That means this guy is linearly dependent. We can find the constants, non-zero constants. Right? We can find the non-zero constant and non-zero constant. So if we pick, for example, pick C1 equals 1, okay? Pick C1 equals 1. We can get C2 equals negative 1. C3 equals what? Equals 5, right? And the C4 equals 0. And we find the non-zero constants. Or you can pick a C1 equals 2, right? And you always can find the non-zero constant. That means that is linearly, the set is linearly dependent. Okay, dependent. So that's the strategy. That's the strategy.